Do you think nuclear fusion on Earth is different compared to fusion in the core of the Sun? If so, what is the difference about it? Now hold that thought, because this video might change the way you think about fusion. I'm Kata, welcome to this episode about nuclear fusion. We've also done a poll asking you if there will be commercial fusion on the grid by 2060. Thank you very much for voting, and I can already tell you that I was surprised by the result. The Lawrence Livermore National Laboratory reported another breakthrough in nuclear fusion.
For the first time, we've been able to create what we call a burning plasma in the laboratory. Burning plasma is a system in which the fuel is mostly heating itself.
The fusion produced about 10 times as much energy as went into heating the fuel. However, that is still less than 10% of the total amount of laser energy required, because the process is highly inefficient. The laser was used for only about 10 billionth of a second in each experiment, with a fusion production lasting 10 trillionths of a second. Harnessing the power of the sun, creating the power of the sun on Earth. What if I told you that headlines like these, sometimes from reputable sources, can actually be misleading? As a reminder, in a nuclear fusion reaction, light nuclei combine into one heavier nucleus, which releases energy. The type of nuclear fusion reaction that occurs inside the Sun is actually different to what we use in fusion devices on Earth. It is the proton-proton fusion. This process begins with protons, which are simply lone hydrogen nuclei, and through a series of steps, these protons fuse together and are turned into helium. So this fusion process occurs inside the core of the Sun, and the transformation results in a release of energy that keeps the Sun hot. The resulting energy is radiated out from the core of the Sun and moves across the solar system. Proton-proton fusion can only occur if the kinetic energy, so the temperature of the protons, is high enough to overcome their mutual electrostatic repulsion. In the Sun, deuterium-producing events are rare. Diprotons are the much more common result of proton-proton reactions within the star, and diprotons almost immediately decay back into two protons. Proton-proton fusion reactions work great in the Sun, but there are a few good reasons why we don't use them on Earth. First, they require a bit more mass than we have here on Earth. Second, the cross-section of a proton-proton fusion reaction is much smaller compared to a deuterium-tritium fusion reaction. Third, the resources for deuterium-tritium fusion are much more abundant on Earth. We'll explain all of them in a bit, but let's look at how fusion reactions work on Earth. In fusion devices, deuterium-tritium fusion, sometimes abbreviated DT, is used. In this reaction, a deuterium nucleus fuses with a tritium nucleus. The result is a helium nucleus, a free neutron, and 17.6 mega-electron volts of energy. That doesn't sound like a lot, considering that a kilowatt-hour is more than double of 10 to the power of 19 mega-electron volts, so it takes a bit more than just one fusion reaction. The Lawrence Livermore National Laboratory made a significant step towards ignition, achieving a yield of more than 1.3 megajoules. Laser light, the size of 3 football fields, was focused onto a target that produces a hotspot the diameter of a human hair. This generated more than 10 quadrillion watts, so 10 times 10 to the power of 15. Awesome, right? The whole world only needs 5,000 megawatt, so million to the power of 9. Wait, what? This experiment generated 2,000 times the power we need for the whole world? True, but only for 100 trillionth of a second. A better comparison would probably be powering 100 American households for a second. Lithium produces tritium when exposed to energetic neutrons, so in fusion reactors, a lithium breeding blanket is placed onto the walls of the reactor to produce tritium.
During operation of ITER, the plasma is in the center of the torus, interacting with the diverter at the bottom. In future tokamaks, we expect every square space to be covered with the breeder blanket. It is needed to replenish all the tritium fuel supply. It shields all the surrounding components, and it needs to exhaust all the energy coming in from the neutrons and transfer it into heat.
But before some of you start writing angry comments about tritium that don't really provide value to other people, you might want to consider hearing me out or taking a look at previous discussions about tritium radioactivity on this channel. You can find them under the previous videos linked in the description below. I really appreciate almost all comments, and I try to respond to each and every one of them. In a nutshell, tritium is a relatively weak source of beta radiation. The beta particle itself does not have enough energy to penetrate the skin. However, it can pose a health risk if taken directly into the body in extremely large quantities. For example, a person would need to take in billions of becquerel before seeing a health effect. Tritium occurs naturally, and its half-life is 12.3 years. Before we look into different types of plasma confinement methods, I'd very much appreciate if you could hit the like button. This will help other people who are interested in fusion to find this video. Nuclei have to get very close to one another in order to collide and fuse. They are positively charged and therefore will repel each other by electrostatic repulsion. If the nuclei are moving very fast, they can overcome electrostatic repulsion. The hotter the molecule is, the faster it will move and the more likely it is to collide. To create and maintain the conditions necessary for thermonuclear fusion reactions, plasma needs to be confined. You may know that there are different plasma confinement methods. In the stars, like the Sun, the confinement is due to the gravitational field that creates sufficiently high pressure. Since there is not enough mass, gravitational confinement is impossible on Earth. The two primary approaches on Earth are magnetic confinement and inertial confinement, and magneto-inertial fusion, which combines inertial confinement fusion and magnetic confinement fusion. If you are subscribed to this channel, if not, please subscribe. You're probably aware that the magnetic confinement is done via toroidal, so donut-shaped devices. The classic one is the tokamak. There are also spherical tokamaks and stellarators. The cross-section might sound a bit theoretical, but besides the fact that we don't have the mass for gravitational confinement on Earth, the cross-section explains a very practical reason for why we don't use the first step of the proton-proton fusion on Earth. The cross-section, usually sigma, is a measure of the reaction probability as a function of the kinetic energy of the reactant nuclei. So a higher cross-section is crucial for the technical and economic viability of fusion power on Earth. As mentioned, in the Sun, fusion occurs via the proton-proton fusion reaction. The first step of the proton-proton reaction is the rate-limiting reaction. It is extremely slow due to it being initiated by the weak nuclear force. That's why you can't find proton-proton fusion cross-sections in cross-section graphs. The average proton in the core of the Sun takes 9 billion years to successfully fuse with another proton. It has not been possible to measure the cross-section of this reaction experimentally because it is so slow, but it can be calculated from theory. So even if we had the same gravity forces on Earth as the Sun, or other stars for that matter, I would not necessarily recommend waiting billions of years for the first step of proton-proton fusion to occur. We're quite lucky that deuterium-tritium fusion is more likely to occur, or in other words, the probability is economically feasible. Let's take a look at the poll result. Thank you very much for voting. About half of the people who voted think that fusion will be commercially available by 2060, and the other half is split between not knowing or believing fusion will not be commercially ready by 2060. As a supporter of fusion research, development, and commercialization, I still think we cannot wait for fusion. To avoid a climate disaster, we have to take action on removing fossil fuel-based technology. Most of all, that means to avoid new carbon lock-ins. This is crucial, no matter if or when fusion will be commercially available. We have the technology for for climate neutrality. The challenge is in taking action. I think it's an enormously complex technological challenge to create economically viable fusion power on Earth. The time frame required to achieve commercial fusion might be difficult to estimate. I'd be very curious to learn your thoughts on nuclear fusion, in particular when it comes to economic viability and commercial readiness of fusion power. For instance, the poll didn't come with an explanation as to why or why not you think that fusion power will be commercially ready by 2060. If you already knew about the cross-section, I'd be curious to learn that. Let me know if you learned anything new in the video. Thank you very much for watching. Don't forget to subscribe and see you in the next video. Bye!